Welcome to Lesson 12.3, and as promised, this lesson will explain the difference quotient and will work you through some of the background for the derivative that we did in Lesson 12.4. So if you look at this graph, I have a simple parabola, and I've identified a couple points on it. This point here, we're going to label x, and then the y value will make f of x. And another point I'm going to label as h. I've gone over h spots here, and then the y value would simply be the f at x plus h. Now if we take both those points and we connect them by a line, that line will go through both of them. And if I wanted to know the slope of that line, here I'm going to change to a pen, then you know what we would do. We would take simply the slope would be the y2 minus y1, or x2 minus x1. Well, if we look at our points, that would be this f at x plus h minus the y here, which would be the function at x. And if we divide that by the x, the second x, which would be the h plus x. Oh, you know what? I did that wrong, didn't I? This right here is not just h, it's x plus h. So let me erase that. I'm glad I did that in pencil. Okay, that's x plus h right there. So that would be the function at x plus h. I'm doing this early in the morning. Here we go. And the bottom x is simply x. All right, so we're subtracting that value. Well, down here in the denominator, you notice that your x's disappear. So you have the function at x plus h minus the function at x divided by h. And that's the difference quotient that we talked about and that you've used previously. Now just look at the picture for a minute. If we take, and let me write this down, if we take the limit as h goes to 0, so as this h gets smaller and smaller and smaller and smaller, it's going to become x, right? We'll get the rate of change or the slope of that curve at that instant, at that specific time. So then we get the rate of change of the curve at that instant. Which we also call this the derivative, right? Derivative, as in 12.4 that we just did. Let's do an example. If I want to find an equation of the slope of a line tangent to this parabola at that point, I would need to go through and plug in this difference quotient and use this formula. So here, if I'm taking the function at x plus h, everywhere there's an x, I have to put x plus h minus the function all over h. Here we go. So the slope is the limit as h is going to go to 0 of this function at x plus h, so I have x plus h squared plus 1 minus the function itself, which would be the x squared plus 1, all over h. Now let's clean that up. square that out. We're going to have x squared plus 2xh plus h squared plus 1. Now I'm going to distribute this negative. Negative minus x squared, negative 1, all over h. And let's see, the x squares reduce, the 1's reduce. Both of the terms in the numerator have an h, so I'm going to cancel. I'm going to pull that out first. That would leave me 2x plus h over h. Then they will cancel. Okay? And you are taking the limit as h approaches 0 of 2x plus h. Well, that equals, as h goes to 0, you're left with just 2x. Now, at the point 2, 5, we simply plug in the 2 for the x. So the slope equals 2x, or 2 times 2, which is 4. And our equation was 2x, right, for the slope. Now let me show you something. If we were to take the derivative, go back up to the original equation, this one right here. If I take the derivative, that would be y prime. I would simply take 2 times the 1, bring that exponent down, so I would have 2, reduce the exponent by 1, 2x. That goes to 0 for the derivative. So my equation is just 2x, and then if I want to know what the value is when x is 2, my value is 2 times 2, which is 4. Now, I'd like you to look at the ease at which we did that. I apologize for not moving that up earlier. Look at how easy that is. And that is one reason we did the derivative in lesson 2.4 prior to this. This sets up what the derivative does and what it means. But you may also take the derivative. Now, we will require some of this, but you don't need to do this for every single problem. But I want you to see you get the same answer. It's the same thing. All right, let's try some other examples, but before that we need to look at some other formulas. You know that we refer to the rate of change, or the y2 minus y1 over x2 minus x1, as the slope. And that is the change in between 2 points, the rate at which that line is changing. Now, you can also denote this as the change in y2 minus y1. You could say f at b, if you have 2 points, f at b minus f at a divided by b minus a. We refer to this form of this same equation as the average velocity. And this takes the change in distance relative to the change in time. So you have a little bit different type of equation. You'll have, you don't just have 2 points, x and y, but they represent distances or time usually. So you're calculating the average velocity. Now, we saw earlier in the notes how similar this is when we work with a graph to this difference quotient, because you are, in fact, taking the difference, again, between 2 points. And this, we determined, was the slope of a tangent line as, looks like line, as h approached 0, or h was approaching x, right? Well, if you take the limit, if you replace your x with t, with time, so similar to this, how we're changing, we're now doing a change in distance, change in time. If I now take x and replace it with time, then I'm taking and I'm calculating the change in distance, again, relative to the change in time. But this time we call it the instantaneous velocity. Because it happens at one specific time of t. So you do have two formulas here. You have the average velocity that I will ask you to calculate and the instantaneous velocity. So this, the average velocity, is going between two periods of time. The instantaneous velocity is at one specific time. What is the velocity at this point, at this period of time? So let's look at two examples for this. First example has a water balloon that is propelled straight up with a launcher. They're kind of fun. The height of the balloon in feet, t seconds after the launch, is given by this formula right here. What is the balloon's average velocity between 1 and 2 seconds? Okay, so there's a clue. Not only did I ask you for the average velocity, but I gave you two periods of time. So you're going to figure out what the function value is at 2 minus the function value at 1 second. And then you're going to divide it by 2 minus 1. Okay, same thing as our A and our B up above in our formulas. Well, you can simply plug in 2, evaluate the function at 2. You can put that in your calculator and see what the value is. But you're going to evaluate that function at 2, and you find out that it is 71, minus that function when you plug in 1 second, gives you 54, divided by 2 minus 1, which is 1. Well, that tells you that that's going to be the average velocity between 1 and 2 seconds is 17 feet per second. Okay? That's not hard math. You just need to remember what formula you're using. Let's look at another example. A window washer, I like this one. A window washer drops a lunch off the scaffolding that's 1,400 feet above the ground. The position of the lunch in relation to the ground is given by this formula right here. Okay, that's how high it was. Remember, this is the gravitational force right here, right? In t seconds and measured in feet. Find the instantaneous velocity equation and the velocity in 7 seconds. Now, if you remember, I'm going to scoot back up here a little bit. When we did this earlier, the first part of the notes, this was the same thing as the derivative. Now, you can do it out long way with the formula, and that's fine with the x plus h minus the function. But you can also do the derivative. Okay, that is what I'm going to do down here. If I want the instantaneous velocity equation, I am simply going to find the derivative of that equation. Well, the 1,400 doesn't have a derivative, but this part does. So that is negative 32t. And then you simply evaluate that at 7 seconds. So this was my first part of the answer, the equation. And then if I evaluate that at 7, I get negative 224 feet per second. Okay, if I plug in 7 right there times 32. That was very quick and easy. Okay. When you come to class, we have a worksheet and a lesson in 12.3, and this is the last lesson in this chapter. I'll see you then.